In this video, we'll discuss the compressible flow. First, we develop the equation for velocity of sound, then Mach number, Mach cone. Then we'll discuss the compressible flow through convergent nozzle, convergent divergent nozzle, Fano lines, Rayleigh's line, and the shock waves. For this one, we require a little knowledge of thermodynamics, so we'll quickly review the thermodynamics first. In the case of perfect gas, pressure is given by rho into R into T. Since Cp and Cv are the functions of temperature only, we can write change in internal energy equal to Cv multiplied by dt, and the change in enthalpy we can write as Cp into dt. So if we integrate this equation, you will get U2 minus U1 is simply equal to Cv into T2 minus T1, and we have H2 minus H1 will be equal to Cp into T2 minus T1. The specific heat at constant pressure minus specific heat at constant volume is always equal to gas constant, and the ratio is represented by gamma. So if we solve this equation using these two equations, Cv is equal to R divided by gamma minus 1, and if we solve for Cp, we will get gamma into R upon gamma minus 1. Two equations we can use for perfect gas, and the process is reversible. For TdS, temperature multiplied by change in entropy equal to change in internal energy plus PdV, and TdS is also given by dH minus VdP. In the case of perfect gas, we can rewrite the first equation as change in entropy equal to du by T plus P by T multiplied by dV. Using P by T equal to R by V, we can write this equation as ds equal to Cv into dt by T plus R into dV by V. Integrating, we get S2 minus S1 equal to Cv natural log of T2 by T1 plus R times ln of V2 by V1. The second equation for entropy change is obtained as dH divided by T minus of V divided by T into dP. Here V by T can be written as R by P, so we'll get ds equal to Cp into dt by T minus R times dP divided by P. Again, we can integrate this equation, and we have change entropy equal to Cp ln of T2 by T1 minus R times ln of P2 by P1. If the process is isentropic, then S2 will be equal to S1, and the law follows is P2 by P1 is same as T2 by T1 to the power gamma upon gamma minus 1. And since the pressure and density are directly proportional, we have P2 by P1 is also equal to rho 2 by rho 1 to the power gamma, where gamma is same as Cp by Cv. So these equations are we are going to use. Consider here a piston and cylinder arrangement, and some disturbance is given. Because of this disturbance, we have a sound wave is generated here. Let's say C represents here the velocity of sound. Let's assume here that the piston here has a small velocity equal to dV, the corresponding density equal to rho plus d rho, and the pressure will be equal to P plus dP. Because of this one, there is a disturbance here which we called as a sound wave, and let's assume here that the final velocity of this fluid here, which was a stationary fluid, so that velocity will be equal to 0, corresponding density equal to rho, and the pressure equal to P. So if we have here a observer, then what is this observer find here? That a piston is moving here as well as the sound wave is also moving. So this time that is the unsteady condition. So we'll convert this unsteady problem into steady problem by considering a control volume here. So this one is control surface. So let's consider here only the control surface. We'll include the velocity of sound inside. Here now at this point here, the velocity is sound velocity equal to C. We have density equal to rho, pressure equal to P. Corresponding to this, since it's a relative now, the velocity equal to dV, we have a velocity here equal to C minus dV. So this become a steady problem now. Let change in pressure P plus dP, and the density equal to rho plus d rho. Now this condition is a steady condition, and what we are interested here, the velocity of sound. And let apply the law of conservation of mass at the inlet and at the exit. Law of conservation of mass for one inlet and one outlet is m dot. At inlet, we have a product of density multiplied by area multiplied by velocity c. At exit, we have density is rho plus d rho. Area is same as equal to A, and the final velocity, because of unsteady to steady, it becomes c minus dv, where dv is velocity of the piston. Now if we expand this, in this case where area will get cancelled, so we have a product of density multiplied by velocity of sound. Let's expand this one. So we have rho multiplied by c, we'll get rho multiplied by dv but negative sign, so we have rho multiplied by dv, then we'll get c multiplied by d rho, and finally we have one more term, that is a product of change in density into change in velocity. So this is the product of two small quantity, it is very small value, can be neglected, and here rho c and rho c is also cancel out. In that case we get here this term, which is same as equal to rho into dv is equal to c times d rho, or we have dv equal to c divided by rho into d rho. Let's call equation number 1. So by applying the law of conservation of mass, we have change in velocity equal to velocity of sound divided by density multiplied by change in density. Now the second equation we apply is the Newton's second law. According to the Newton's second law, we have net force acting along the x direction equal to rate of change of momentum along x direction, that is the final velocity minus the initial velocity multiplied by mass flow rate, but you have to take this product along the x direction. So this time we have pressure multiplied by area is a positive force, so this side will take as a positive direction. So we have P multiplied by A is a positive force, and P plus dP will develop the negative force. So we have minus of P plus dP multiplied by A. Mass flow rate, you can use any of this equation. So I will prefer the first equation, which is a simplified form, that is the density multiplied by area multiplied by c. We have a final velocity here is c minus dv, and the initial velocity here is c. So if we expand this, we will get p into a minus p into a minus dp into a. Here this c and this minus c cancel out, and we get here minus of rho into a into c into dv. Here pa and minus pa will cancel out, minus minus sign we can omit, and area will be get cancelled. So what we get is dp equal to product of density into c into dv. At this stage we can put equation 1 here, so we have to put equation 1. In that case we'll get dp equal to rho multiplied by c, and dv can be replaced as c divided by rho into d rho. So rho and rho will again cancel out. We get here c square, so we have c square equal to dp divided by d rho. So we have velocity of sound is given by the equation under root of change in pressure to change in density. So small disturbance is generated here, because of this the sound wave is generated. And in case of isentropic flow, we have a generalized equation is given as PV to the power gamma equal to constant, and we have reciprocal of density is same as specific volume. So this equation can be written as P into rho to the power minus gamma equal to constant. Now this equation can be very well replaced using this term by partial differentiation. So if we partial differentiate, we'll get rho to the power minus gamma into dp plus minus gamma into rho to the power minus gamma minus 1 into p into d rho, and right hand side is constant, so derivative that term will be equal to 0. Now this entire equation will divide by rho to the power minus gamma. In that case we'll get dp minus of gamma rho to the power minus 1 into p into d rho will be equal to 0, or what we get is dp equal to gamma, this rho will be adjusted as p by rho into d rho, and what we know here is this equation of velocity of sound. So from this we can generate dp by d rho is equal to gamma times p by rho, and since p by rho is same as RT, we have this equation is gamma multiplied by R multiplied by T. So if you know the temperature and if you know the gas constant and the value of gamma, then we can calculate the velocity of sound in that particular gas. So right now we have developed two equations. By definition, we have velocity of sound is change in pressure by change in density. And in the case of gas, this equation is same as under root of gamma times R times T. Remember, this equation only applicable for isentropic flow. Recall that the bulk modulus is also defined in the case of fluid mechanics as change in pressure upon change in volume divided by original volume but negative sign. And another definition is change in pressure divided by change in density divided by original density. So from this also we can develop the equation for dp by d rho, that is the velocity of sound, as beta by rho. So we have third equation that is applicable is beta divided by rho. So if we know the bulk modulus, then you can very well calculate the velocity of sound. So right now we have three equations. The velocity of sound originally defined as the change in pressure by change in density. In the case of liquid or solid, we can use this definition because beta is very well defined in the case of solid as well as in the case of liquid. And in the case of gases, we can use the definition of under root of gamma times RT. So this definition is valid in the case of gases. In this case, you have to use the value of T as a static temperature. Later on we'll define the stagnation temperature, but whenever you have to calculate the velocity of sound, you have to always use the static temperature, and that is also in Kelvin because we have used here a thermodynamic relation. Consider here air at a temperature equal to 300 Kelvin. We have gamma is equal to 1.4 for air and the value of R is equal to 287 joules per kg per Kelvin. So this one is ordinary condition, and in ordinary condition the velocity of sound can be obtained as under root of gamma times RT, that is 1.4 multiplied by 287 multiplied by 300. So at ordinary condition the velocity of sound in air will be 347.2 meter per second. If we consider a water at ordinary condition, in that case we know the density of water is 1000 kg per meter cube and the bulk modulus for water is 2.1 gigapascal. We can very well calculate the velocity of sound in water, but this time we'll use the definition of under root of beta by rho. So beta by rho will be same as under root of 2.1 into 10 to the power 9 divided by 1000. That is very close to 1450 meter per second. That will be approximately 4 times the velocity of sound in air. And in the solid mechanics we already know that we have Young modulus is equal to 3 times of bulk modulus. Actually symbol K is used for bulk modulus into 1 minus 2 times of mu, where mu is Poisson ratio. As far as the steel is considered, we have Young modulus will be equal to approximately 296 gigapascal. Mu is equal to 0.3. In that case we can very well calculate the value of beta, which is equal to 296 divided by 3, 1 minus 2 times of 0.3 will be 246 gigapascal. We can very well calculate here the velocity of sound in steel, that will be under root of beta by rho. And temporarily let assume the density will be equal to 7800 kg per meter cube. In that case we have beta will be equal to 246. So we have 246 into 10 to the power 9 divided by 7800. Calculate the velocity of sound in steel is close to 5615 meter per second, which is almost same as 4 times of velocity of water. So this is 4 times the velocity of sound in water, or will be 16 times the velocity of sound in air at ordinary condition. Take a simple numerical here to calculate the velocity of sound for a crude oil having a density equal to 800. So we have rho is equal to 800 because Hg is given as 0.8. 0.8 into 1000 is 800 kg per meter cube, and we are given the bulk is 1.5 gigapascal. So we have velocity of sound in oil is under root of beta by rho. So we have under root of 1.5 into 10 to the power 9 divided by 800. So velocity of sound in oil is 1369 meter per second. What is the velocity of sound through the oil or specific gravity 0.8 and the bulk modulus of oil is 0.8 times the bulk modulus of water. So this time we have given the density of oil equal to 800 kg per meter cube and the bulk modulus of oil is 0.8 times the bulk modulus of water, which is 2.1 gigapascal. So we have bulk modulus of oil is 1.68 gigapascal. To find the velocity of sound in oil, we have a same formula, that is under root of beta by rho. So we have under root of 1.68 into 10 to the power 9 divided by 800. So in this case, we'll get the velocity of sound in oil as 1449.1 meter per second. A sonar signal bounces off a submarine and returns in 15 seconds. Average temperature of ocean water is 10 degrees Celsius. Its isentropic compressibility is 2.07, which is same as bulk modulus. What is the distance of submarine? Take specific gravity of sea water as 1.02. So this one is a submarine which is at a certain distance from the free surface level, and we have a sonar signal at the sea surface which generate the sound wave. The sound wave will generated from the sonar signal will reach to submarine and will return back to the sonar signal. The total time required is 15 seconds. So the time required to reach from the sonar signal from sea surface to submarine is 7.5 seconds with a velocity of sound equal to c. So let's say we have s is equal to c into t. Depth of submarine is c into t. Now this time we have given the specific gravity of seawater as 1.02. So we have density of seawater is 1.02 multiplied by 1000. That equal to 1020. We have bulk modulus is given as 2.07 into 10 to the power 9 Pascal. So velocity of sound will be under root of beta by rho, which is equal to under root of 2.07 into 10 to the power 9 divided by 1020. That is 1424.3 meter per second. Hence, the depth of submarine is equal to S is given by product of C multiplied by T. We have C is equal to 1424.3 multiplied by 7.5 equal to 10684.3 meters or 10.68 kilometer. To what change in pressure liquid or specific gravity 1.2 should be subjected to cause reduction in volume by 1%, and velocity of sound in liquid is given as 1500 meter per second. So we have density is specific gravity multiplied by 1000 is 1200 kg per meter cube. Velocity of sound c equal to 1500 meter per second. This time our working fluid is liquid, so we can calculate here velocity of sound as under root of beta by rho, and beta is known to us is given by dp by dv by v but negative sign. Hence we can calculate here the change in pressure once we know the value of bulk modulus. And this time we have given the reduction in volume by 1%. So we have dV by V is minus of 0.01. So first of all we'll calculate here the velocity of sound as under root of beta by rho. Since here we know the value of velocity of sound, we are able to calculate the value of beta. So if we square it on both sides, we'll get 1500 square equal to beta divided by rho, which is 1200. From this we'll get the bulk modulus equal to 2.7 into 10 to the power 9 Pascal. Now we'll use this definition of beta, and from this we can calculate a change in pressure. So we have change in pressure equal to minus times beta multiplied by dV by V. So minus and minus become positive, and we have 2.7 into 10 to the power 9 multiplied by 0.01. That is 2.7 into 10 to the power 7 Pascal, or we have 27 megapascal will be the required pressure change.